Hello, and today we're going to talk about modeling some realistic situations using functions. And oftentimes we're going to use multiple functions to model different parts of a scenario. So the best way to do this is just jump right into an example. So we've got this character Finn who's filling his pool with a hose. Water is coming out of the hose at a rate of 20 liters per minute. So that means every minute that hose is putting 20 more liters of water in the pool. However, it's a sunny day and the water is also evaporating, but it's probably evaporating really slowly. Yeah, it says it's evaporating at a rate of 0.1 liters per minute. So that's sort of the rate that we're losing water out of the pool. So this problem's probably going to want us to write some functions involving Finn filling up his pool. So we've got the function f of m returns the total volume of water that came out of the hose m minutes since Finn started filling the pool. Okay, so let's write an equation for f of m. Okay, so we need to be thinking, how fast is the water coming out of the hose? Well, that's at the rate of 20 liters per minute. So if we multiplied that by how many minutes that the water is running, then we would get how much water has come out of the hose. So like over here on the side, let me do a quick example. So let's say, the water is running out of the hose at 20 liters per minute. Let's say the hose has been on for 3 minutes. So if we multiply the rate at which the water is coming on the hose, if we multiply that value by how long the hose has been on, see, look what happens here. These minutes cancel. We're left with 20 times 3, which is 60 liters. So that mathematically makes sense with these units canceling, but it also intuitively makes sense. If the hose is running at a rate of 20 liters per minute, that means in the first minute you'll get 20 liters. Then in that second minute, you'll get another 20 liters. And in the third minute, you'll get another 20 liters. So you'll have gotten 60 liters of water altogether over those 3 minutes. So we can use this idea to write the equation for the function f of m. It's going to be 20 times m. 20 being the rate at which the water is flowing out in liters per minute, and then m is the number of minutes. When you multiply the number of minutes and the rate at which the water is coming out of the hose, you get how much water has come out of the hose. So finding this evaporation function, the function E of m returns the total volume of water that evaporated from the pool m minutes since Finn started filling it. So this function will be E of m, and then I'm going to use the same logic here. 0.1 liters per minute, that's the rate at which the water is leaving the pool. I multiply that by the number of minutes, and I'm going to get how much water has evaporated. So there are my two functions, f of m representing the total water that Finn has put in the pool from the hose after m minutes, and E of m, the total amount that's evaporated after m minutes from the pool. So now they want us to write a new function w of m, and this function w of m returns the total amount of water that's in the pool m minutes since Finn started filling it. Great, so basically the hose is filling up the pool, we've got some water slowly evaporating off, and then of course, what if there was already some water in the pool when Finn started filling? We'd have to take that into account as well. So suppose the pool had 10,000 liters of water in it when Finn started filling it. So now this is sort of a notational issue. They want us to write the formula for W of m in terms of f of m and E of m. So this in terms means that when I write this equation for W of m, on the right-hand side, I need to be seeing f of m and e of m. I need to be using those two functions and any other values that I need to account for how much water is in the pool. Okay, so let's think about this. How much water is going to be in the pool? Well, we started with the 10,000, so let's throw that down there. Then we're going to add in the amount of water that Finn is filling up from the hose. That's f of m. So if I add f of m to the 10,000, that's the 10,000 is what I start with. F of m is all of the water that's come from Finn's hose. But then remember, the water is also evaporating, so we're going to have to subtract off how much water has evaporated. So that right there, that is W of m, representing the amount of water in the pool after m minutes, after Finn turned on his hose for m minutes. And that's in terms of f of m and e of m. So notice this is highlight this super ultra important phrase because this comes up all the time. This in terms of. So whenever you're writing something, this W of m, in terms of these two things, that means you're going to have an equation W of m equals, and on the other side you need to be seeing this f of m and e of m and other things, and you need to sort of piece everything together to make a true statement. So these sort of things are challenging notationally. There's a lot of symbols here, and just intellectually challenging of thinking about the scenario. So they require a lot of practice. We'll have to do a lot of problems to get really good at these. So let's see what the last part is here. We want to write the formula of W of m. We want W of m to be in terms of, there's that phrase again, m. Okay, so I know what W of m is in terms of f of m and e of m. I'm just rewriting my last answer. But I want W of m to be in terms of m, which means now the only thing I should see on the right-hand side of my equation is the letter m and some numbers. So now I basically want to just start to do some substitution. Like, what is f of m? F of m, I came up with that function on the second slide. F of m is simply 20m. And what's e of m? E of m is 0.1m. So now look what I've done. I've written W of m in terms of m. That means that the only variable I see over here on the right-hand side is m. Whereas before, I was seeing f of m and e of m. I just want to see the variable m combined with other constants. And notice I can see m over here multiple times. I can have, m's, m squareds, log of m, whatever is necessary for the situation. But the only variable I should be seeing is m if I'm writing W of m in terms of m. Only variable I should see on the right-hand side of the equation. And if I wanted to clean this up, I could collect like terms here. 20m minus 0.1m, these are like terms. So the 20m minus 0.1m, that's 19.9m. And then I've got that plus 10,000. And look at that, that's a linear equation. I just wrote that in slope-intercept form. Great, but as far as the question goes, either of those would be totally acceptable answers. So these questions are challenging, but I know that we're up to the task. Good luck.